Now, if in this previous slide we have seen that the definition of a smooth vector field. So, in this slide we are giving particular point P. In a point P we are assigning a vector xp, and this assignment is smooth. Okay. Now we come to the question, what is the mean by the smoothness of this assignment? So here we answer this question. Okay. Take any coordinate neighborhood U of P with local coordinate xi. Then we can write xq is equal to summation of I if I q del xi q for all q belongs to U. Well, we said that the P assignment to xp is smooth if this coefficient fi are smooth with respect to any local chart in any smooth atlas of M. Therefore, by the vector field we always mean the smooth vector field, and set of all vector field on M is united by chi of M. Here we are given an example. Let M is equal to R2, this is the equivalent plane, and xi is equal to del xi. P goes to del xi p. Then xi is a smooth vector field on R. Now we state the interesting question of vector field. Can you find a no-word vanishing vector field on even dimensional sphere S2A? It is not possible, and this is proved by the great mathematician J. Milnor. It is a very deep result in algebraic topology, but now there is a simpler proof. Now we say about the derivative of a differential map. We have two smooth manifold M1 N and their nth function M2N, which is differentiable. Now the derivative of the function f at the point P is the map df of P, which acts on Ppn and to the set Pfpn, and this map is defined by the following relation. Let V is a vector field, the vector tangent vector, then there exists a smooth gamma, which initial point is P and its tangent vector at the initial point is V. Then a composed gamma is smooth curve in N with initial point Fp. Now define dfp of the point V is equal to f composition gamma dash of 0. Now this is the picture. Here M and M, the yellow one is M and the green one is N, and f is a function and P is a point in M and f is a point in N. Then this function smooth if we have a curve at the point P, that we have curve gamma of t with initial vector with tangent vector at the point P is t phi dt. So here we are talking about the function dfp. Here v is d phi dt, so it goes to the d phi dash dt, where phi dash t is equal to a composition of phi of t. Here the function phi dash is a curve in the manifold N. For P belongs to M and V belongs to TPM, the vector dfpv is a tangent vector at the point Fp. Therefore, dfpv can be seen as the derivation of the all smooth function of the manifold N, and it is defined by dfpv into z, where z is a smooth function of n is equal to b of z composition of f. Now the chain rule. If we have two functions, f from m to n and g from n to k, then the composition g compose f is a form n to k and it is also differentiable. And the derivative rule is the derivative of g compose f at the point p is d of z fp composition of d of fp. Now, the differentiable of a function f from m to n at the point p is a linear map, and this can easily be proved since if it is differentiable at the point p. So, for two vectors u comma b, the d of fp u plus b into g is equal to u plus b into z composition f for any function, smooth function z of n. Therefore, d fp u plus b of z equal to d of z composition f plus u of g composition f. This is equal to d of fp b into z plus d of fp u into z, which implies the linearity property of this map. Now, for scalar multiplication, if we take the scalar c, then d of p cb into z is equal to c of dfp into b. It can easily be seen. So hence dfp is a linear map. Okay. Now, if f is a diffeomorphism from m to n, then for every point this derivative map at the point p is an isomorphism. This can be proved that since f is a diffeomorphism, so it has an inverse, say g. Hence, g composition f is equal to identity on n and f composition g is identity of n. So, by using the chain rule, we get that d of g composition f is equal to d of j at the point d of g at the point fp composition d of f at the point p, and d of composition g at the point q is equal to d of f at the point p composition d of g at the point q, where p belongs to m and q is f of p. D composition at the point d of g at the point fp composition d of f at the point p is identity map at the point m at m, and d of f at the point p composition d of g at the point q is identity map. So which implies that dfp is an biaxial. Therefore, dfp is an isomorphism. Now we come the definition of integral curve. Let x be an vector field and p be a point. A smooth curve is set to an integral curve from vector field x passing through the point p. Its initial point is p and gamma dash t is equal to x of gamma dash t. So basically it means x is an integral curve of a vector field is a curve whose initial point starts at the point p and whose tangent vector to each point is same as the vector field of each point of the curve. Now here is the picture. Okay, here is the gamma is curve and its tangent vector of the point gamma is same as the vector field of this curve. Now you have given an example. If it is equivalence 10, then x equal to x of del del y minus y of del del x, and p comma e comma b is the integral curve through p. So to find the integral curve of this vector field, we need to solve the following differential equation, and the solution of the above differential equation is this one. And by this simple calculation, we show that it is a circle with radius root over x square plus b square and centered at the origin. Now the existence field. We have a vector field and a point. Then there exists epsilon, which is very small, and an integral curve such that the curve has the initial point p and its tangent vector is the same of the vector field. Okay. Now the uniqueness theorem. Basically, the uniqueness theorem tells us that we can find a maximal integral curve of a vector field as a given point. Okay. Now let the x belongs to phi of m and gamma 1 and gamma 2 be integral curve. If we can find a point in this two domain I1 and I2 such that gamma of a is equal to gamma 2 of a and then gamma 1 is equal to gamma 2 on I1 intersection I2, and this curve and the curve defined by the gamma of t is equal to gamma 1 t while t belongs to I1 and gamma t to gamma 2 t while t belongs to gamma 2 t is an integral curve, and this curve gamma is called the maximal integral curve. Now, a vector field is said to be complete if the domain of the definition of all its maximal integral curves through points of M are the whole real line, otherwise it is said to be incomplete. Okay. Now suppose M is a manifold and X is a complete vector field, then for each point P there is a unique integral curve such that whose initial point is P. Okay. Now from this one can define the function as follows. For any t belongs to R, then can define the phi of t from M to M is defined by the point P which goes to gamma of t. Okay, so the map phi R into M to M defined by phi of t p is equal to gamma is equal to phi of t p is a smooth function. The map the defined previously is called the flow of the vector field X, and the above map satisfies the following property. This is the first one is the computation rule. This is the gamma t into gamma phi t into phi s of the point P is equal to phi t computation phi of s is equal to phi of t plus s p. This family phi of t is called one parameter group of transformation of M.